Hi, welcome to lecture 4.3 of the SAGE-based course on Monte Carlo methods. We were just looking at the variance and population variance and the population mean of the Bernoulli random variable. Now let's look at the population mean and variance of the uniform 0,1 random variable. Once again, the expectation of this random variable is given by the integral x f of x dx, where f of x is the probability density function of uniform 0,1 random variable, and it's in this case just 1 inside the interval 0,1, and we can find its antiderivative and evaluate it as follows, and we find that the expectation of x is half. Expectation of the second moment is again 1/3, where we simply integrate x squared against f of x dx. Finally, the variance of the uniform 0,1 random variable is expectation of x squared minus expectation of x the whole squared, which is just 1/3, minus half squared, which is 1/12. So let's look at another example of expectations where you're looking at winnings on average. So now think about playing a game where we draw x according to a random variable capital X, and then say you get paid r of x. So r is some reward function, a function of x that says what your reward is when x is drawn. Then your average winnings for the game is the sum or the integral over all possible values of x of r of x times the chance that the random variable x is going to be equal to x. So formally we say capital Y, let capital Y be r of x, the reward random variable. Then the expectation of y is nothing but the expectation of r of x, which is simply r of x times df of x. Integrated over the entire real line. So with this idea of the winnings on average or the expected reward, we can now talk about expectations of rewards of various random variables. Now, probability is an expectation. So to understand this, think of the reward function r of x as the indicator function of the event A. Okay, so recall that the indicator function of the event A is simply 1 if x is in A and 0 otherwise. So if x is a continuous random variable, then the expectation of the indicator function of A is simply the integral of the indicator function times the df of x. So if it's a continuous random variable, then it's simply the integral over a f of x dx, and that's simply the probability that x belongs to a, which is nothing but the probability of a. So similarly, the expectation of the indicator function of a for a discrete random variable, once again, is simply the probability of a. So this argument simply says that probability is a special case of expectation. That is, the probability of an event A is simply the expectation that A will occur. So let's take a uniform 0,1 random variable x. Now what would you say the probability that an observation of this random variable is less than half? That is, what is the probability that the random variable x is less than or equal to 1/2 if x is a uniform 0,1 random variable? Then let's use SAGE to simulate some observations and look at the relative frequency of these observations being less than 0.5. So recall that uniform 0,1, the built-in function in SAGE will produce numbers between 0 and 1. So if I keep calling this again and again, I'm going to get different numbers. So we're going to use that as our basic simulator of the uniform 0,1 random variable. So the first variable in this code is assigning observations of interest. So initially it's 0. This is counting the observations of interest. So finally, the second variable, number of obs, is the variable to control how many observations we're going to simulate. Okay, so let's sort of bring this guy here to make the comments a bit cleaner. Now, observation of interest is simply the value that we are going to ask if the random variable or the simulated random variable is less than. So that's the half, 0.5. Now, here is our for loop. The for loop simply goes through the range number of observations, so 0 to number of observations minus 1, and in the body of the for loop we're simply asking this statement where, let's make this a bit smaller. Okay, so that's a little better. So in this if statement we are going to simply ask if the simulated uniform 0, 1 random variable is less than or equal to observation of interest, and if so, we're going to increment this counter. Okay, and finally, when this for loop is done, we will print the string, the relative frequency of x less than or equal to observation of interest was the count of interest divided by number of observations. This RR simply converts that rational number into a multi-precision floating point real, and we're only showing it up to 3 digits of precision. So let's evaluate this. Now we get that the relative frequency of x less than or equal to 0.5 was 0.502. That means 502 of the 1000 simulations were less than 0.5. If I evaluate this again, I'm going to get different numbers. The relative frequency of x less than 0.5 is 505 now, 0.505. So 505 this time are less than 0.5. This time 488 were less than 0.5. Okay, so the point here is that I want you to appreciate that the probability that the random variable is less than or equal to some given value, such as 0.5, is the relative frequency of the event that x is less than 0.5. So we can do the same for the Bernoulli random variable. I'm just going to let you do this on your own. So if you just recall from before, randint 0, 1 will give us random numbers between 0 and 1 with equal probability. So we're going to simply play the same game here for this Bernoulli half random variable and find out that the relative frequency of this random variable being 1 was 0.490. That means 490 of the 1000 observations produced this Bernoulli half random variable to equal 1. Okay, so now it's 481, and this time it is exactly 500 of the 1000. And if I do it once more, I get 460 of the 1000, taking the value exactly 1. Another way of thinking about the Bernoulli half random variable is that it has a discrete uniform distribution over the finite set 0, 1. So it can take on a finite number of values, and the probabilities of observing either of these two values are equal. So the de Moivre 1 over k, 1 over k, dot, 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 1 over k random variable is our new discrete probability model. In this one, we will allow the random variable to take on one of k possible values. So 1, 2, 3, all the way up to k for some fixed number k with equal probability. Okay, so a de Moivre 1 over k, 1 over k, dot, dot, 1 over k random variable x has a discrete uniform distribution over 1, 2, up to k, and these k possible values are equiprobable or equally probable under this random variable. So one such example is rolling a die. So x is the number on the die, then k equals 6. And another example is the New Zealand Lotto game. There are 40 balls in the machine. They're numbered 1, 2, 3 up to 40. The number on the first ball out of the machine in a particular lotto trial can be modeled as a de Moivre 1 over 40, 1 over 40, 1 over 40 random variable. We say that a random variable x is de Moivre 1 over k distributed if its probability mass function, or PMF, is the following: f of x semicolon. So this vector is the vector of parameters. Okay, so the same way the parameters follow the semicolon. So little f of x is simply 0 if x is not one of these elements in the set 1 through k, and it is the value 1 over k if x is one of these elements. So we can now find the expectation of this de Moivre, equiprobable de Moivre random variable with 1 through k outcomes as x times probability that x equals x, which is 1 times 1 over k plus 2 times 1 over k plus dot 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 k times 1 over k. We can pull the 1 over k out and realize that 1 plus 2 plus dot 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 up to k is nothing but k times k plus 1 over 2. And this simplifies to k plus 1 over 2. So the expectation of the de Moivre random variable with k equiprobable outcomes between 1, 2, up to k is k plus 1 over 2. The second moment, the expectation of x squared by a similar argument, is 2k squared plus 3k plus 1 over 6. And finally, the variance is k squared minus 1 divided by 12. So we could use the Sage randint function to simulate the number on the first ball in a lotto draw. So randint 1, 40 will do that trick for us. So it will produce a number uniformly at random between 1 and 40, as I'm doing now. So this allows us to simulate the first ball that pops out of a lotto machine. This brings us to the new topic of product experiments. So far we have talked about having one random variable or one observation of a random variable. Often our experiments involve a number of separate observations. Say we flip 2 fair coins. We assume that the 2 flips are independent and that for each coin we can define a random variable which takes the value 1 if the coin lands up heads and 0 otherwise. We will label the random variable for one coin as x1 and the random variable for the other coin as x2. What we have is 2 independent and identically distributed, or IID, Bernoulli half random variables x1 and x2 in this case. So when we have 2 IID, independent and identically distributed Bernoulli half experiments, we can refer to them as x1 and x2. If we are interested in the results of these separate coin tosses, we can think of a random vector, or capital X, to be the ordered pair x1, x2. So if we think of the 2 random variables, ID random variables, as a random vector, then there are 4 possible results for this product experiment. Namely 0, 0 if both coins land tails, 1, 0 if the first one is heads but the other is tails, and 0, 1 if the first one is tails and the second one is heads, and finally 1, 1 if both coins land heads. Because the 2 random variables are independent, the probability that x1, x2 takes the ordered pair value 0, 0 is simply the probability that x1 is 0 multiplied by the probability that x2 is 0. And this comes from the independence assumption that the 2 random variables are independent of one another. So probability that x1 is 0 is half, and that x2 is 0 is also half, so we multiply them and get 1/4. Similarly, we get 1/4 for the other 4 possibilities for the random vector x1, x2 being 1, 0, 0, 1, or 1, 1. In general, with n IID random variables, we have a random vector x given by x1, x2, dot, 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 up through xn. And we will need to work with concepts of n IID random variables pretty soon. And this is the formal idea behind product experiments. So the product comes here because of independence. Okay, so that's when we multiply the probabilities. That's where the product comes from, multiplying probabilities. due to independent assumptions in our experiments.